So we will continue our discussion of depth first search, of DFS. And so before that, let me just revisit the code that we had for DFS. So the key, extra data maintained in depth first search in DFS that we will use are the start or the discovery times and the finish time. And so just to second, sorry about that. Right. Okay. So if you recall, in DFS, for every vertex, we have a discovery time, which is when DFS is called. That's when it gets visited. And what we also have is a finish time, is that when the procedure finally finishes, we store the time, and the time is sort of ticking at each step. So every time there is a discovery or there's a finish, time increments, and so all the discovery times and finish times are distinct. And DFS on G, the whole graph, is simply done by running DFS on all unvisited vertices. Now, one of the key properties we're actually, the key property over here is the Parentheses Theorem that basically says that the discovery times and the finish times sort of form a parenthetical statement. And moreover, so if you think of these as intervals, there's the interval, the lifetime interval of DFS of U and DFS of V. If the interval for V is contained in the interval for U, then V is a descendant of U in the DFS forest. So these this we had discussed. And then we had this other property called the unvisited path theorem that said consider the time in which U is visited, or you could say just before U is visited, if there exists a path of unvisited vertices from U to V. So everything except U is unvisited, then V is a descendant of U in the DFS forest. So meaning if you found a path from U to V, all of which are unvisited except for U, because U is visited at that time, if all those vertices are unvisited, then V is a descendant of U. Right? So this is the unvisited path theorem. And so these were the two properties that we discussed of DFS. Any questions about these? All right, let us continue. So now we are going to talk about the main topic for today is topological sort and actually more complex versions of that. So consider a directed graph, a DAG. Consider a directed graph. A directed graph is a DAG. That's a directed acyclic graph if G is directed and has no cycles in it. So for example, if you construct a dependency graph between code, where you might have vertices being files, and an edge means that file U needs to be compiled before file V. So for example, if this piece of code has include foo.c, then foo.c has to be compiled before this code. So we would put an edge from foo.c to that code. And this is called a dependency graph. A dependency graph should not have cycles, because if it has cycles, then the code cannot be compiled. And often you will see that if you write code of this form and you run a utility like make, it will say there's a cycle in the dependency graph. So the first question, problem one can ask is, given a graph, determine if it's a DAG. Now suppose it is a DAG, then what we would like is an order of compilation. We'd like to know in which order should we compile the files. And this is a very interesting example, because if you think about what these hash includes are, this is essentially the adjacency list. This is like the in neighbor list, right? Because the hash includes tell you who are all the in neighbors of this file. So topological sort essentially means finding an order of compilation. So what you would like to do in a DAG, so suppose you have a DAG of this form. So here's our DAG. We would like to order the vertices in such a way that the edges always go from lower order to higher order. So we can think of that as labeling the vertices v1 to vn. So think of it, if the vertices were initially called 1 to n, you want to relabel them. So I'm just going to call it v1 to vn. So you label the vertices v1 to vn such that for all edges, E goes from lower in the order to higher in the order. So for example, in this case, a topological sort could be given by, I'm just going to label the vertices 1 to 6. So I could label this 1, then this is 2, 3, 4, 5, and 6. Does everyone see that this is a valid topological ordering?
Isn't 4 going into 3?
Oh, I'm sorry. 4 is going into 3, so this is actually not a valid topological ordering. Thank you. So this would be 3, and that would be 4. Thank you. Good catch. Yes. So just making sure that, yes, this is a valid topological ordering. So sorry for that mistake. Okay, any questions about a topological ordering?
How is it valid? Can you explain a bit more?
So look at every edge. Every edge points from a lower number to a higher number. Right? Go to every edge. It points from a lower number to a higher number. So this gives you like an order of processing. So you could basically process 1. You could compile 1, then compile 2, then compile 3, compile 4, compile 5, then compile 6. So if you were to think of these as actually code, like each of these is a code, and 1 points to 6 means that, 6 includes 1. And 6 includes 5. By 6, I mean like the code represented by that vertex has a hash include for this code.
Can 6 goes to itself?
I'm sorry?
Can you go 6 from 6 to 6?
What is that? What do you mean from a 6 to 6?
Like to itself?
So this is a DAG over here, right? So these are the edges that so this is your entire graph. That's your graph.
Okay.
You need to order the vertices of the graph in such a way that the edges go from lower in the order to higher in the order.
Okay, I see. Okay.
And when we say DAG, we don't allow an edge from a vertex to itself, do we?
No, we don't allow that because that would also be a cycle.
Thank you.
That would also be a cycle. In general, I am considering, let's just say if in this case, the graphs are simple. So there are no self loops and there are no parallel edges. So this is for a simple graph.
Are all orders equivalent, or are there like some orders are more useful for some tasks? Like here, for instance, my first instinct would have been to put the lowest number on the singleton with no incoming edges.
I mean, you can define some sort of objective measure, like some objective, and then try to optimize over orderings, which people do. You can, depending on what the problem is, it might end up being solvable. It could end up being polynomial. It could end up being hard, NP-hard. So that's an interesting topic of algorithms. Questions? Okay, just to make sure that everyone is following and mostly awake, I'm going to ask you a question. The topological ordering of a graph that is of a DAG. DAG, I should say. DAG is unique. And so A is yes, B is no.
Can I see the prior graph again?
Sure. Okay, so there seems to be, while the majority have it right, there seems to be some confusion on this point. The topological ordering is not unique because, indeed, I can give you this graph for which there are two. So let's just, let me number these vertices 1, 2, 3 internally. Okay, so sorry, maybe I should draw this a little bigger. So that's 1, 2, 3. This is the numbering just of the vertices itself. So here are topological orderings. 1, 2, 3 is a valid topological ordering. So is the ordering 2, 1, 3. Right? So these are both valid topological orderings, meaning that it's earlier in the order to later in the order. All the edges point that way. Right? So there's no edge from 2 to 1, but there's one from 2 to 3 and 1 to 3. 1, 3, 2 is not a topological ordering. Is this clear, right? So the topological ordering of a graph, it's an ordering of the vertices. I mean, I did a labeling over here, but you can also think of it as an ordering of the vertices. It's to basically permute the vertices in an order so that the edges go from lower in the order to higher in the order. Second question is the topological ordering can be unique. True, false. Okay, so it seems most of you got this right. Yes, that's true, simply because, if your DAG looked like this, then of course the topological ordering is unique. You have to take this vertex, then this, so on and so forth. So essentially, this is like saying that, for those of you who have some math background, essentially a DAG is a partial order, and this is a total order. And so a topological ordering is essentially sort of an ordering of the elements of a poset, which is equivalently a DAG. Okay, so now we have another problem that we can ask. Which is, given a DAG G, compute a topological ordering. And so this is, in some sense, a very important problem for which DFS is almost like it's like the canonical answer for this problem. Okay, any questions so far? Any questions so far?
I have a question that maybe is a little bit out of scope, but I was wondering, in the case of a topological order like the one we defined a little bit earlier, the 1, 2, 3, 2, 1, 3, can you sort of define certain steps of that order to occur concurrently? Or is that kind of beyond it? That's kind of outside the idea of a topological ordering?
That's a good question. That's outside. So in some sense, what you want to say is that like you can process 1 and 2 concurrently.
Mm-hmm, exactly. Yeah.
So you're asking, that's a bigger question. So that is in some sense trying to classify topological orderings in certain sets. Mm-hmm. So you can say like, this is in some sense like they're equivalent because you could switch 1 and 2 and you still have a topological ordering.
Exactly. Yeah.
So that's beyond the scope of this. It's an interesting question. Like you can try to come up with situations where you have sets of vertices that are interchangeable, and a lot of that will take you down through. So essentially, if you think about it, when are sets interchangeable? They're interchangeable when you don't have paths between those vertices.
Mm-hmm. There's no interdependence.
Yeah, but you have to be careful because, for example, what if you did this, right? Suppose there was another vertex here, 4. Right?
Mm-hmm.
And I ordered it 1, 4, 2, and 3. Now I cannot switch 1 and 2.
Yeah.
But if the ordering was 1, 2, 4, 3, then I could switch 1 and 2.
Mm-hmm.
So, the definitions, you have to be careful as to what you define, right? I mean, you might think 1 and 2 are interchangeable, but they're only interchangeable in this ordering. They're not interchangeable in this ordering.
Oh, I see what you're saying.
Right?
So there's almost like constraints depending on how you.
So the question is a little more complicated than what you have, but you'll see that we will do, when we talk about strongly connected components, some issues like this are going to pop up. So hold on. Hopefully, I'll cover some of those things.
All right.
I will cover that today. Okay. All right. So let us now continue with this problem of this is the second problem, but how do you determine if G is a DAG? Turns out there's a fairly simple solution. And for that solution, first let me give you a definition. I'll say an edge E UV is a back edge. Okay, it's a back edge of the DFS forest, or I should say of a DFS forest, if V is an ancestor of U. So a back edge, so if you take the DFS, let's say you take the DFS forest, that's a back edge. It points from a descendant to an ancestor, right? Because this is pointing from U to V. So V is an ancestor of U. U is a descendant of V. Or equivalently, if U is a descendant of V. Okay, does that make sense? So that's what a back edge is. Okay, so if a back edge is present, can the graph be a DAG?
No.
Why not?
Because you can just take the path from U to V, or I guess V to U, and then the back edge is a cycle.
You get a cycle, exactly. So if this is, so here you have a back edge which was U to V. Now this is an ancestor, so obviously there is a path in the DFS forest, and that gives you your cycle. Right? So I'm just going to write this down as a claim, which says that if there exists a back edge, then G is not a DAG. Equivalently, G is a DAG implies that there is no back edge in any DFS forest. Right? If there's a back edge, well, then you have your cycled. So obviously, if G is a DAG, then there is no back edge. There cannot be a back edge. Any questions about this? This is an exercise.
How would you prove that, Professor?
You would prove it basically by saying that, suppose there's a back edge UV. V is an ancestor of U. Now, because V is an ancestor of U, if you look at the DFS tree, there is a path from V to U. Because V is an ancestor. And so now you have a path from V to U and an edge UV that goes back. So that this entire thing is a cycle because you can start at V and end up at V.
So the proof is through BFS?
Good question. Good question. This is also true in the BFS forest.
Okay.
There's nothing about DFS that I used here.
I see.
So you might ask, why am I doing this with DFS? I'm going to show you why, because DFS will compute topological orderings. But that's a good question. So this is also true for BFS. Okay. So if there is a back edge, then G is not a DAG. What is harder to prove is the converse. If there is no back edge in a DFS forest. So it's somewhat stronger. It says, but if there's no back edge in any DFS forest or in a DFS forest, then G is a DAG. Okay, so before, I want to make sure that you understand what this is saying. So it says if there's a back edge, then G is not a DAG. And if there is no back edge, then G is a DAG. So this gives a simple algorithm, a linear time algorithm. So hence, we can determine if G is a DAG in linear time by running a single DFS. And this is very important. If there's nothing else you take away from today but this, I would still consider that I've done something useful. I've taught you something useful. Run DFS, check if there's a back edge. If there is no back edge, then G is a DAG.
How do you know for any edge whether it's a back edge? Just by looking at the...
Good question. How do you determine if an edge is a back edge?
I guess you can look at the times of V and U to see if they're descendants.
So if you know that there is that's a good, exactly. So just to bring this back up again, the start and finish times tell you whether something is a descendant or not. And so you can simply look up the times to determine if V is an ancestor or descendant of U. right? So the start and finish times are extremely useful here. So you just get the start and finish times, and then you go ahead and run this. Any questions?
The back edge, that's like in the graph itself, right? Not in the DFS.
So the edge is from the graph, but it's a back edge with respect to the DFS forest. Back edge does not make sense unless you have a specific DFS forest in front of you.
All right, that makes sense.
Right? So you run DFS and then you go and check for every edge of the graph if it is, let me write this down. Okay. So what is the procedure? So I'll just say first you run DFSG to get the DFS forest, which I will denote as script F. To get the DFS forest and the discovery and finish times. And for every edge, E equal to UV, right? So this means that U is pointing to V. So you're trying to determine if V is an ancestor of U. So if the interval discovery of V finish V contains the discovery of U and the finish of U, then just output G is not a DAG. And if you run through this loop, you can just output G is a DAG. Right? Okay? So this is just linear time, right? Because this is just a constant time operation. This is O of 1 time. Right? So this runs in basically the first step runs in O of m plus n. The second step runs in O of m. Third is, of course, just constant time. So you have O of m plus n, total, linear time.
I have a question.
Yeah.
You said the package doesn't make sense without the DFS? But
without a DFS tree, right? It's because the definition is with respect to a DFS forest. Ancestor and descendant only make sense if you have a specific tree that you're looking at.
Sure, but if you have an ordering and however else you have come up to it, you can still define packages with that too.
With respect to any ordering, you said.
Basically, like I'm thinking, sure, in the definition we're using the word DFS, and I understand that, but we can define it differently. And I guess the problem would be to check if it's a package where if you don't have the timings, right? Does that make sense? So
I mean, yes, you could define the back edge with respect to any ordering.
Okay.
Yes, you're right. But this is the thing is that that's somewhat of a more restrictive definition because the DFS forest is not an ordering.
Sure. Mm-hmm. But we only need basically the ordering or times or a way to detect packages.
Correct, but then you see that the reason that the times satisfy this condition is because they're coming from DFS.
Sure. Yeah. Okay. Thank you.
Right? I mean, you need the parentheses theorem to be able to do this.
Mm-hmm.
And you need for the parentheses theorem, you get it from the properties of DFS. Does that make sense? So you're really using the properties of DFS.
Yeah, it makes sense.
In this. But there was a question, very valid question asked before, that the same is true for BFS as well. The same is true for BFS as well. But you cannot, there is no notion of start and finish times there, but there are ways of determining whether, who's an ancestor of what. And, that's a good exercise to do, right? You're given a tree and given an edge, you have to determine whether, one is an ancestor of the other. So yeah, you can do this efficiently with the right data structures. But okay, so far so good. All right. How do we prove this? Because this claim, the converse, is more challenging to show. It turns out that it's easier to prove the contrapositive. So we'll just take the contrapositive.
Oh, I can't see.
I'm sorry. Take the contrapositive. What is the contrapositive? G is not a DAG implies the DFS forest has a back edge. So let me draw out some pictures and then we can figure this out. So you have some cycle here. Right? So G is not a DAG, so there is a cycle. How are we going to argue that there is a back edge? So maybe we want to show one of these edges is going to be a back edge. Why is that?
So we're trying to figure out if it has a back edge right now?
We want to prove that it has a back edge, right? Because we're trying to prove this theorem with this claim, which is that if there is no back edge in a DFS forest, then G is a DAG. Now, it turns out it's easier to prove the contrapositive of this statement. So hopefully you understand what I mean by contrapositive. I mean, contrapositive is P implies Q. The contrapositive of that is not Q implies not P, which is an equivalent statement. So let me take the statement, G is not a DAG implies DFS forest as a back edge. I'm going to prove this statement. I want to prove this statement here. To prove this statement, I'm going to take a cycle because I know G is not a DAG. And if I can argue that one of the edges of the cycle is a back edge, that completes my proof. And if I can prove the contrapositive, then of course I'm proving the main statement. Is that clear? Any
Yes, but I
questions?
don't see how that's possible to do a back edge on the cycle.
How it's possible
To have
So
a
I'm claiming
back edge?
one of these is going to become a back edge.
Oh, one of them. Okay.
That's all I need to show, right? Because that shows me the existence of a back edge. So okay, so maybe let me say this, right? So what do I want to argue? I want to prove that if G contains a cycle C, so this is a directed cycle, right? Some edge of C is a back edge. Any thoughts about which of these edges is going to become the back edge?
Any of them?
Awesome.
Yeah, all of them could.
The f-
back edge.
Well, all of them are not going to become back edges.
The first and the last,
First and the last according to what?
like starting point.
the first node that gets visited in the cycle.
Okay. The first node that gets visited.
Yes, that was what I meant. Yeah.
Okay. So the first node gets visited. So what's the back? Which is going to be the back edge? So let me call this first node visited U.
The one,
Actually, let me call it
201.
V. Let me call it V. I'm sorry. Let me call it V. Okay. Which is going to be the back edge here?
The one before it.
Incoming edge.
This one.
Yeah.
Yes.
Okay. So I'm going to call that U. And so your claim is that UV is going to be the back edge. This is the first
Visited.
visited. Okay, why? UV and Y, right? 3 letters. Why is that going to be a back edge?
Because if you keep going back to the ancestor of the nodes connecting to V, you will reach V.
Yeah, but the definition of a back edge, I mean, but that doesn't mean it's a back edge in the DFS forest. These edges might not be edges in the DFS forest or the tree.
Well, can we use like the path theorem from yesterday?
Okay, so what is the path theorem? Good.
Since like there's no visited vertices between V and U, we know U is a descendant.
Exactly, right? So precisely, good. So what we use is the unvisited path theorem. Except, okay, sorry, so U and the roles of U and V are switched, but it basically says if you visit a vertex and there exists a path of unvisited vertices to some other vertex, and that other vertex is a descendant. And that is precisely what you do here, right? You'll say, consider the first visited vertex. There is a path of unvisited vertices to U. So U is a descendant of V, and hence UV is a back edge. I'll write this down, but I hope you see this, right? So it's not that you're going to follow these edges specifically, because maybe none of these edges are actually present in the DFS forest. It is conceivable that none of these edges are present in the DFS forest. Who knows? Maybe there's actually an edge that goes from here to here.
Can that be possible if the graph doesn't have the edge going there?
Of this edge?
Yeah. Like
maybe there's some other path.
Edge there.
There could be some other path that goes from here to there, and DFS decides to go that way.
How can there be some other path if the graph does not have that path, and like the tree has that?
So I'm just saying your graph may have many more edges than the cycle itself.
Okay, so like it's not the complete graph.
No, what I drew here was not the entire graph. I only drew the cycle.
Okay.
Right, this is the cycle C. There could be a bunch of other edges. Who knows what the graph looks like? You're just trying to say that if the graph contains a cycle, some edge of that cycle is a back edge. And it may be the case that actually only one of these edges is a back edge. Right, you could have something where maybe DFS decides to go there and then come back here and then go there and then come back here. It could do any kind of weird zigzagging thing where it visits all of these vertices, but in such a way that none of these are back edges. The only way you get a back edge is because finally U becomes a descendant. And U might become a descendant because of some other path, not because of these edges. So I just want to emphasize the idea that someone had, which is like, well, just follow these edges backwards. It seems like it's a reasonable idea. And it is the first instinct of something to do, that you want to follow those edges backwards. But the problem is that you don't know what DFS is doing because DFS is ordering things in whichever way it does. So you really do have to use the unvisited path theorem. And that's why I stated this theorem. So these are like the little tools that you need to prove things. The unvisited path theorem and the parentheses theorem. I will add that the unvisited path theorem also holds for BFS by essentially the same proof. Although it's, you have to sort of modify things. The proof over here uses the parentheses theorem, but you can do it otherwise. You can do it in other ways. And the unvisited path theorem also holds. So essentially, whatever is being said here also holds for the BFS forest. But we'll see that there are properties of the DFS forest which we will exploit. Okay, so I'm just going to write this down and then I will answer any questions about this. So I'll say, let V be the first visited vertex in C. So what does that mean? It simply means that V is equal to the argmin of W in C of the discovery time of W, right? It's the minimum. It's the one that has the minimum discovery time. So let V be the first visited vertex in C. Let U be the vertex before V in the cycle C. So UV is an edge. When V is discovered, or I should say visited, when V is visited, there is a path of unvisited vertices from V to U, which is basically follow the cycle C, right? Follow the cycle C to get the path. Hence, by the unvisited path theorem, U is a descendant of V. So U is a descendant of V, so UV is a back edge. And that completes the proof, right? So it's fairly straightforward once you have the unvisited path theorem. Otherwise, it actually becomes quite complicated. Otherwise, in some sense, you will implicitly prove the unvisited path theorem. Okay, any questions? Okay. So we've resolved the first problem. We have resolved the problem of determining if a graph is a DAG. Right? What we need to do now is to solve the second problem, which is, given a DAG, compute a topological ordering. And this is now where DFS shows its power. It's a remarkably simple yet powerful statement. It says the reverse order of finish times is a topological order. This is remarkable because no matter how you do DFS, and I'll say for any run of DFS, right? So even though DFS may order things in the most adversarial way possible, the reverse order of finish times is a topological order. Any questions about just the statement itself?
Isn't that sort of a contradiction to the statement then? Because if we prove that there's some order was not valid, we could say that we can create an ordering like that.
No. So okay. So you're right. Sorry, I should have said this. For assume G is a DAG. For G being a DAG. That makes sense. So if you run DFS on a DAG, then the reverse order of finish times is a topological order. Does that answer your question?
Yeah.
For any run of DFS, I should say on a DAG. Sorry, yes. Questions? Okay, so before I tell you how to prove the statement, this now gives us our linear time algorithm. So hence, a topological order, a topological ordering of the vertices of a DAG can be determined in linear time. So technically, you could of course sort the finish times, but then the sorting might take you n log n. So you could do it a little bit more carefully by saying, basically run DFS of G And when any vertex finishes, you just push, when any vertex V finishes, you push V onto a stack. And essentially, you know, the stack S has the topological ordering. Is this clear? So we need to prove the theorem. Again, like when you use the tools of the parentheses theorem and the unvisited path theorem, these proofs become quite simple. But it's not obvious to know how to use them, and that's why, you know, I would like you to do these as an exercise. Now, I'm going to prove, I will not prove the full theorem. I'll prove something which is almost the full theorem, and then you can complete the proof yourself. So I'm going to prove a claim, and if you do an induction on this claim, the theorem will be evident to you. And when I write what I'm going to write, the theorem will be evident. So assume, you know, G is a DAG. For every edge UV, so you have this edge UV, the finish time of U is greater than the finish time of V. Okay? So hopefully you kind of see the argument that if this claim is true, the theorem is, then you can prove the theorem. Essentially, you can do some kind of induction on this to prove. Actually, you don't even need an induction. It's immediate. Yeah. Sorry, go ahead.
Oh, I was just wondering why you would need induction.
No. The way I defined it, defined topological ordering, it's actually immediate. So okay, so this claim essentially implies the theorem. Okay. Okay, so what is the proof? So we will do something here that is, again, a very important aspect of many proofs, especially in graph theory. We will do what's called a case analysis. The case analysis based on the discovery times. Okay? So case 1 is that the discovery time of U is less than the discovery time of V. So U is discovered first. Okay, so I'm just going to draw this picture here. U, V, U is discovered. Okay, so what's the proof?
Well, based on the finish time, V has to be a descendant of U.
Exactly. And just to complete what you were saying, so why is V a descendant of U?
By the parentheses theorem.
The parentheses theorem, right? You have to be, well, no, you have to be a little bit more careful than that. Let's because I think there is, if I'm not mistaken, there's one thing that you're missing. So this is the discovery of U, and here is the discovery of V.
Oh, could you move the paper down, please?
Oh, I'm sorry, yes. So, by the way, so I just saw something in the chat, which normally I don't. So please, if you have a question on the chat, just pause and ask me. But it says you're using a stack, so V gets added on the stack after U. So the stack over here is no. So at this point, this stack is only with respect to finishing. So one doesn't know exactly what's going to happen over here. So you need to make an additional argument to show that V is an answer, V is a descendant. So what is the argument? Sorry, am I making sense here? So why is the finish time of U more than the finish time of V?
Doesn't this just follow directly from the parentheses theorem?
Well, the parentheses theorem only implies that it's a parenthetical statement. So maybe this discovery, the finish time of U could be here.
But we know that it's not. From
Why?
It's written.
The finish time.
Oh, sorry. I thought that was an assumption.
Yeah, no. This is you're trying to prove it. How do you know that the finish time is not before the discovery time?
Isn't it just by nature?
Sorry, there were multiple people who spoke. So any one of you go.
So because you are visiting V?
When? V is unvisited at this point.
It's just by nature of how we assign the times incrementally.
No,
Right?
not necessarily, right? So how do you know that U is not going to finish before V?
Because V is a child of U. So if it's not visited.
No, but why is V a child? It's just this is just an edge. This isn't an edge of the of the DFS forest. It's an edge of the graph.
Well, but when we process U, V has not been visited. So it has to be added at that time, right? So the discovery of V, like the discovery of the V happens in the while loop.
Okay, yeah. So
when we're
but
processing U.
so it's the white path theorem. It's the unvisited path theorem again.
So it's not because it's a DAG.
It has nothing to do with the fact that it's a DAG.
Oh, okay.
Right? I mean, it's because of this, right? Actually, we proved essentially that argument in the proof when we did it before. We argued exactly that when you have an edge from U to V and U is visited, then V becomes a descendant of U. So we have to invoke this theorem. It's not just obvious that V is going to be a descendant of U. I mean, it is because of the argument that in the while loop eventually it gets considered, yada, 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 but that is exactly what the unvisited path theorem says. I want to emphasize this point just so that, you understand that this is how we're going to be formal about this. So we say by the unvisited path theorem, right? Because, I should say, since UV is an unvisited path, from U to V at the time U is visited, V is a descendant of U. Right? And so therefore, because it's a descendant, and then by the claim earlier, right? So we proved this earlier. This implies that the finish time of U is going to be greater than the finish time of V. And this is because U is an ancestor, right? So V is a descendant, U is an ancestor, and hence this is true. Is this clear?
Yeah.
Yeah.
Yep.
I forgot we made the assumption of the finish time.
Sorry, we made an assumption on the discovery time, not in the finish time. This is what we want to prove. This is not an assumption.
Oh.
The assumption is on the discovery time. This is the case. We're doing a case analysis. We're saying the discovery time of U is either less or it's going to be more. So in the first case, the discovery time is less. I'm going to pause here, allow you to, I'll give you a minute, read through this and make sure that you understand.
So we're assuming for certain there does exist a path between U and V.
No, U and V is an edge. But an edge is a path. Right? An edge is also a path.
So can we then shouldn't we only be able to use that theorem if the unvisited path theorem if we know for certain the finish time of U is greater than the finish time of V?
No, the unvisited path theorem says consider the time at which U is visited. If there exists a path of unvisited vertices from U to V, then V is a descendant of U. So at the time U is visited, because the discovery of U is less than the discovery of V. So when U is discovered, V is unvisited. And so this is now a path of unvisited vertices from U to V.
Right.
So by the unvisited path theorem, U is a descendant, and then therefore it holds. But you use the case assumption. That's why this is an unvisited path, because the discovery of U is less than the discovery of V.
I get it, but it just feels like the unvisited path theorem is we're kind of using the unvisited path theorem to kind of restate what the unvisited path theorem says, which is the finish time. Like I get this is true, but it kind of seems like we're restating what the unvisited path theorem is, and therefore
we are restating we are restating the theorem, but we're not proving the theorem. We're using the theorem.
Oh, so I mean, logically it makes sense to me, but like the sentence that says since UV is an unvisited path from U to V at the time U is visited, V is a descendant of U. This doesn't make sense at all.
By the unvisited path theorem, you are using this theorem. You're applying the theorem says if a particular condition holds, then something else holds. So you're saying this particular condition, the if clause holds, hence this clause must hold.
Okay.
Right? I mean, you are applying the theorem.
Okay.
Okay, just to be clear, I want to poll you right now and ask you, like, A is I'm following and B is I'm confused. Right? I've launched a poll. A is I'm following, B is I'm confused.
Well, I got a question.
Yes, go ahead.
Can you tell us what's the difference from this claim and with the Parentheses Theorem of DFS? It seems similar to me.
This theorem says for any edge, the finish time of U is greater than the finish time of V. The Parentheses Theorem doesn't talk about edges. The Parentheses Theorem, let me just pull that up 1 second. The Parentheses Theorem says for any two vertices whatsoever, this is the relationship between the discovery times and the finish times, right? Either one interval is nested in the other or they're disjoint. It doesn't say anything about what happens for the relative finish times of edges themselves. Indeed, this is not true if the graph is a cycle. This is not true if the graph is a cycle. And for a simple example, consider this. Okay? So what's going to happen? Let's just do this as an example, right? So I'm going to call this U, V, W. All right, and so let's use parentheses for that, square brackets for this, and that, and let's start the DFS over there. Okay, so what are the parentheses going to look like? Can someone tell me? It's pretty simple with the parentheses.
Nested.
They're all nested, right? So you have this, then this gets visited. So then you have that, then this gets visited. You have this, then this finishes, and that's what you have. Which edge violates this condition?
The squiggly brackets, or from W to U.
From W to U, exactly. So this is W to U. This edge is violating this condition. So the parentheses theorem tells you nothing about the, well, I mean, it gives you this condition, but the parentheses theorem does not imply that for any edge, the finish times have to actually satisfy a particular ordering, right? The WU edge is a counterexample.
Well, it is it is proving that the finish time of U would be greater than B, but like for our claim, it's not valid because we are assuming that G is a DAG. Is that why?
Correct, exactly. So you need to use the fact that it's a DAG to prove this condition.
Okay, yeah. That's why it doesn't work. Otherwise, it works. Like W would finish earlier than U. But like for our condition, because we are assuming it's a DAG, that is why, because like it's a cycle, so it's not working for us.
True, that's why it's, but I'm just saying that I'm just giving you a counterexample to this. Somebody asked, isn't this equivalent to the parentheses theorem? And I want to say, no, it's not equivalent because the parentheses theorem holds here, but this condition does not hold.
Yeah, so like the parentheses theorem does not consider the graph to be a DAG or not.
It doesn't assume anything, and hence, you cannot use the parentheses theorem by itself.
Okay.
Indeed, in case 1 also, we have not used the fact that G is a DAG. Okay, so now let me continue. So this is in case 1, when the discovery time of U is less than the discovery time of V, the white path theorem tells you V is a descendant of U, and hence the finish times are going to have the right order. U is going to finish before, V is going to finish before U. So case 2 is that the discovery time of V is less than the discovery time of U. Okay, so now this is the discovery of V, and this is the discovery of U. Okay, now what?
The finish time of V would be less than the discovery of U.
Well, if that's the case, then you've actually invalidated the theorem. You want to actually prove that. Sorry, say that again. Say that again.
I said that the finish of V would be earlier than the discovery of U. Like
Why?
the square bracket would come before the parentheses.
Why?
Because there's no outgoing edge and there won't be any recursive call.
There's no, there could be outgoing edges from here, right? Who knows what's there? There could be all kinds of things there. This isn't the entire graph, right? This is merely an edge of the whole graph.
Doesn't V just finish before the discovery of U?
Why?
We know that U can't be a descendant of V, otherwise UV would be a back edge.
Good. So now there. So now we need to complete the proof. You're almost there. So there's one more thing you need to do, and then the proof is done. Just prove it by contradiction.
Should we use the same theorem?
Which theorem?
Unvisited path theorem.
You don't need the unvisited path theorem here because there is no path to be considered here.
What about the reverse order one?
Sorry, go on.
The reverse order, if we consider it in reverse order from finish time.
But that's what you're trying to prove. You can't use what you're trying to prove.
Oh, wait. Right.
That's
Because
what you're trying to prove that. What you want to prove is just this condition on the finish times.
so because U isn't a descendant of V,
Yes.
then V has to finish before you can. Sorry, then V has to finish before you can start.
V has to finish
That's,
before you can almost, yeah, but you see that there's a slight gap between what you want to argue and what you like the statement and what you're saying. You're right. I mean, that is the key. The key is that U is not a descendant of V. So you just put the parentheses theorem on top of it and you'll be done. So let me just prove by contradiction.
Wait, why do we need the parentheses theorem? Why can't we use, I mean, in the previous case, we had this theorem about like vertex V is a descendant of U if and only if. Can we just use
oh yeah, you're right. Yeah, that
the negation
yes,
of that?
Yeah, you can just use that. Yeah. But yeah, so you need this claim. You need the claim about, you're right. That's like a special case of the parentheses theorem, really. But let me state your argument equivalently by just saying that, okay, the discovery of V is less than the discovery of U. Suppose for contradiction, the finish of V is less than the finish of V. So this is for contradiction's sake. Suppose that was the case. So the finish of U was less than the finish of V. So what you know is that the finish of U, which is here, is less than the finish of V. This implies, so by the claim earlier, not the parentheses thing, you're right. I mean, by the claim earlier, U is a descendant of V. So UV is a back edge, but G is a DAG, so this is a contradiction. And that completes the proof. Right, this is just saying that suppose finish of U was less than the finish of V. So write that down. Finish of U is less than the finish of V. Well, then by the claim earlier, maybe I should just show you that claim again. Sitting in my notes here, that basically vertex V is a descendant of U in the DFS forest if and only if these conditions hold. The discovery of U is less than the discovery of V, and the finish of U is greater than the finish of V, which is exactly the conditions over here, with U and V switching their roles. And so U is a descendant of V, but if U is a descendant of V, then the edge UV is a back edge, but G is a DAG, so it contains no back edges. That's a contradiction. This completes the proof. Any questions? Okay. Any questions at this point? It's a good time to ask me because I'm going to continue to the next topic then. All right. So the whole point, I mean, okay, let's just step back. So even if you didn't follow the nitty-gritties of the proof, the reverse order of finish times is a topological order. And essentially, for every edge UV, the finish time of U is greater than the finish time of V when G is a DAG. Okay? All right. So we did topological orderings, but some of the questions which came up at the beginning are about what different topological orderings, different orderings of vertices. And so the next generalization of that is the concept of strongly connected components. So I'm just going to assume that G is a directed graph, directed simple graph. No parallel edges, no self loops. Although you could do all of whatever I'm saying here is equally valid for those settings, but just to keep things simple, technically, I guess, okay, so maybe one doesn't even need this, just directed graph. So I'll say U is strongly connected to V if there is a path from U to V and a path from V to U. So note that in a directed graph, the notion of being connected is asymmetric, right? In a directed graph, if you take two vertices, U could be connected to V, V could be connected to U, but both might not hold. Strongly connected means that there is a path that goes from U to V and a path that goes from V to U. Okay, and I'm going to denote this by this sort of double squiggly arrow. And so the single squiggly arrow means U has a path to V. But the double squiggly arrow means that U is strongly connected to V. Does that make sense? Any questions about that? Questions? Okay. Now the key is that this relationship is an equivalence relation. Can anyone recall, what is an equivalence relationship?
Symmetric, reflexive, and transitive.
Symmetric, reflexive, and transitive. Right? So it's going to satisfy all of these conditions. So first is it's symmetric. So why is it symmetric? U being strongly connected to V is equivalent to V being strongly connected to U. Right? And that's there. U is strongly connected to itself because a vertex sort of by default, it has a path to itself, just that single vertex. And it's transitive because if U is strongly connected to V and V is strongly connected to W, that implies that U, is strongly connected to W, right? So it's transitive. It is reflexive, and it is symmetric. So what happens if you have an equivalence relationship amongst us in a set?
It induces a partition.
It induces a partition. Right? So V, which is the vertex set, can be partitioned into equivalence classes and these classes are called the strongly connected components. So this is like connected components, but a directed. So I can define this sort of directly. I'll call it an SCC is a maximal set of vertices such that for all UV in the set, U is strongly connected to V. So what does this really mean in terms of a graph? So you could have some component here, which is like a directed cycle, where everything can connect to everything. And then you have something else over here, which is also some directed cycle. And then you may have some edges that go from here to here. So each of these is a separate strongly connected component. It's like connected components, except that in each component, you can go from anywhere to anywhere. And here you can go anywhere to anywhere. But you cannot go from anywhere in here to anywhere in here. Between these components, it's sort of like a one-way relationship. But within the component, you can go from any vertex to any vertex following a path. That's what a strongly connected component is. And the equivalence relationship is just there to argue that this partition makes sense. One can partition the vertices into strongly connected components. So if you want to think of this as, and this isn't, especially in these days of social networks, it's very easy to justify lots of graph questions. So think of this being like a Twitter network, right? And this edge means that U follows V. Now, typically what you have in an information network, which is like Twitter, is you have some people who broadcast and a bunch of people who listen. And then you have little components of people who talk to each other. So maybe these are like, people who go to the same university, they all talk to each other. Right? So this is a strongly connected component. But there are some celebrities here, so that everybody follows those celebrities. And the celebrities probably follow each other. So how do you separate this portion from this portion? The strongly connected components is like a simplistic way of doing it. I mean, there are more fancier ways of doing it. But this would be one of the most basic ways. So you find out sets of vertices so that within the set, it's not that all follow each other. It's just that there is a path that goes from any two vertices. Between any two vertices, there exists a path that goes from one vertex to the other, and vice versa. But between two vertices, one in this set and one in this set, the shaded set, the edges only go in one direction, and the paths only go in one direction. Does this make sense? The definition of strongly connected components? Questions?
Yeah, so if the two strongly connected components have a bidirection or a back edge from another strongly connected component, then they will form a bigger strongly. Yeah.
Exactly. Then the whole thing would form a strongly connected component. Because you can get from anywhere in here to anywhere, and anywhere in here to anywhere. And so what you'll do is from here, you'll get to this part. You'll try to get to somewhere in there. From there, you can always get to this, and then you can get back in. So you'll essentially have paths from anywhere to anywhere in the entire set. It's a good point. And this is going to be my next exercise.
Okay, thank you.
Okay, good. So does that make sense?
If you wanted to find partitions of partitions, would you look outer in or inner out? As in, like, would you kind of look at two different partitions and see how you could maybe partition them together, or would you start with a single partition and try to, partition that itself?
You mean try to refine the partition?
Right.
You mean you're asking of how to find the strongly connected components?
More so when you have a partition of
So you're not having a partition of partitions. You're refining a partition is different from having a partition of partitions.
Okay.
I mean, when you say partition of partitions, you're thinking of a set of partitions.
Right.
That I don't think is what you're doing, right? You're thinking of just the partitions of the vertices and trying to relate them to each other.
Okay.
I mean, if I'm not mistaken, I mean, maybe I'm not following exactly what you mean by partition of partitions.
No, you're right. Like a set of partitions, but to me, that set seems like because all these partitions have something in common as well, that set in itself is a partition.
Okay, so let's step back, and I mean, just make sure that you understand what strongly connected component means, and you recognize that the strongly connected components partition the vertex set of a DAG, right? Because it's an equivalence relationship. Pictorially, what you have is your graph looks like this, right? So your directed graph, any directed graph, can be partitioned into strongly connected components. So here, you can essentially go from anywhere to anywhere. Here, you can go from anywhere to anywhere, so on and so forth. What is the relationship between the strongly connected components? How do the edges go between this? There's a structure. There's a word for how the edges go. What happens?
It's a DAG.
It's a DAG, exactly, right? The edges here must form a DAG. So I'm going to formalize this in just a bit. So here are a few claims that I will leave as exercises. Okay, so the first claim is that given two SCCs, S1 and S2, I'll say two distinct strongly connected components, S1 and S2. There cannot be edges from S1 to S2 and from S2 to S1. The more general claim, I mean, this is a specific claim, more general claim is that I'm going to write something here. Consider the graph called H on SCCs. So what this means is that there is a vertex in H for every strongly connected component of G, and if there is an edge in G from SCC S1 to S2, there is an edge S1, S2 in H. Like, this is the construction of H. So I'm just describing, consider this graph. So you basically take this, you take every strongly connected component and you kind of merge it into a single vertex. So you've merged the strongly connected components into vertices, and then you put an edge from one strongly connected component to another if there's an edge between. So there could be many edges between these, but you'll just put one edge. But remember, this edge and this edge mean different things. This edge means that there's an edge going from this component to that component, from S1 to S2. Whereas this edge, the second edge, means there is an edge going from S2 to S1. And these are two different things. So we can construct the graph on SCCs where there's a vertex in H for every strongly connected component. And if there's an edge from SCC S1 to S2, right, from the strongly connected component S1 to the strongly connected component S2, then there's an edge S1, S2 in H. And the claim is that H is a DAG. Essentially, because if there's any cycle in H, then you can actually merge the strongly connected components into a larger one. And strongly connected components are defined to be maximal. So anyway, so the thing is, the problem is given G, find all strongly connected components. More generally, construct H. So you want to construct the DAG of SCCs, and this is called the DAG of SCCs. Okay, so this is the problem. And somewhat remarkably, again, DFS solves this problem, and you only need to run DFS twice. So 2 runs of DFS can find all strongly connected components. This is sort of a classic result in graph algorithms. And again, you know, it uses the finish times, but then it does a little bit more on top of it. We have a few minutes left, so I will just end here because I don't want to sort of get into this algorithm. And I'll take any questions that you have about anything that we've done today.